Okay, hello Math 111 students. As I've mentioned, we'll be turning our attention to online learning for the time being. I'll be creating several YouTube videos going over these notes that I have posted to Blackboard. So let's get right to it. Where we had left off was talking about the multiplication rule in Chapter 5. And so here is the general multiplication rule. And you want to be using the general multiplication rule whenever you're selecting multiple items from something. We had done problem 27 in class, and so let's take a look at problem 28, which is another example of the multiplication rule. It says, due to a manufacturing error, 3 cans of regular soda were accidentally filled with diet soda and placed into a 12-pack. Suppose that 2 cans are randomly selected from the 12-pack. Part A, determine the probability that both contain diet soda. Okay, so because there are multiple items being selected, we want to use the multiplication rule. There are 3 cans in the 12-pack that are diet soda, so 3 over 12 would be the probability that the first can selected would be a diet. Now, once a can is selected from the 12-pack, 11 cans are left in the pack, and if you already selected a diet soda first, then 2 diet sodas would be left in the 12-pack, and so 2 over 11 would be the probability that that next can would be a diet soda. When you multiply these numbers together, you get 1 over 22, or roughly about 0.045 if you're using decimals. I had mentioned that I didn't really care if you were using fractions or decimals, at least in class. Part B, determine the probability that both contain regular soda. Okay, so again, we're going to use the multiplication rule because we're selecting multiple items here. There are 9 cans that are regular soda in the 12-pack, so 9 over 12 would be the probability that the first can selected is regular soda. Once you select a can, there are 11 cans left in the 12-pack. If you've already selected a regular soda first, then there are 8 regular sodas still left in the 12-pack, and so you'd multiply by 8 over 11 if you want that next can also to be a regular soda. Okay, multiplying these numbers would give us 6 over 11, or roughly about 0.545 if we're using decimals. Would this be unusual? No, this would not be unusual because the probability is not a very low number. Now, it would be unusual for both cans to be diet soda, since we have less than a 5% chance of that occurring. That's likely not to happen. Okay, so here's the next page. Part C of that says to determine the probability that exactly one is diet and the other is regular. Okay, now in this problem, we need to think of the ways that we can select these 2 cans. We just want one to be diet and the other to be regular, so that could happen by selecting a diet soda first and then a regular soda second, or selecting a regular soda first and then a diet soda second. Either one of these 2 cases means that one is a diet and the other is a regular. Now, or is a key word that I've mentioned there, so that would suggest that we're going to be using the addition rule in the calculation. Of course, the next thing that we'd want to know is if we have mutually exclusive events going on. It would be enough to just look at the first can selected to determine that. So if you were to select one can from the pack, it is not possible for the can to be a diet and also a regular. And so because that cannot happen, then yes, these are mutually exclusive events. Okay, and all that means to us is that we're just going to simply add these 2 probabilities together. Remember that mutually exclusive just means that the 2 events cannot occur at the same time. So the probability of getting a diet first and then a regular second would be right here. There are 3 diet sodas in the 12-pack, so 3 over 12 would be the probability of selecting a diet soda. Once you've selected a can, 11 cans are left in the pack, and all the regulars are there. All 9 of them, so 9 over 11 would be the probability that that next can is a regular. Plus the probability of getting a regular first or a diet second. Okay, so there's 9 regulars in the 12 pack. 9 over 12 would be the probability of getting a regular soda. And then once you've selected a can from the pack, 11 cans are left in the pack. All the diet sodas are still there though, all 3 of them. And so 3 over 11 would be the probability that that next can would be a diet. When you simplify these two fractions, you get 9 over 44. And when you add them together, when you simplify, you'd get 9 over 22, which would be the answer. Now in this problem, of course, we're using the multiplication rule because we're selecting multiple cans from the pack, but we are also using the addition rule. Although they didn't say the word or, that's something that we'd still have to think about in the problem because we have 2 cases to consider, and that'll sometimes happen. Okay, problem 29 says, according to the U.S. Bureau of Labor Statistics, there is a 5.2% probability that a randomly selected employed individual has more than one job. Also, there is a 50.4% probability that a randomly selected employed individual is male, given that he has more than one job. What is the probability that a randomly selected employed individual is a multiple job holder and male? Okay, so and is a key word there, which would suggest that we're going to be using the multiplication rule. Now remember, the formula for the general multiplication rule is the probability of A and B is equal to the probability of A times the probability of B, given the fact that A has occurred. Okay, so I'm using that general formula there that was on the previous page, and I'm using that for these 2 events here. The probability that somebody has more than one job was given to us. That's 5.2%, or 0.052 if we're using decimals. And then in the next sentence it says, also there is a 50.4% probability that a randomly selected employed individual is male, given that he has more than one job. Okay, well that's this other probability then. So basically in this problem we just need to simply multiply these 2 numbers together and we get roughly 0.026 if we round to 3 digits. Would it be unusual to randomly select an employed individual who is a multiple job holder and male? Yeah, that would be pretty unusual since we have less than a 3% chance of that occurring. It's likely not to happen. Okay, another important term that we're going to have to know in these sections is the term for independent events. The definition says that 2 events, A and B, are independent if the occurrence of event A in a probability experiment does not affect the probability of event B. 2 events, A and B, are dependent if the occurrence of event A in a probability experiment does affect the probability of event B. Okay, so in other words, you can be given some information here, suppose that you are given event A, and that's really not going to matter because if you find the probability of B, you'll end up getting the same number had you been given event A. Same thing in this other equation. Just because you're given event B, that really doesn't matter. A and B are independent. So if you find the probability of A, you'll get the same number had you been given this information. It's kind of like this. Suppose that you were sitting at the desk and you have a deck of cards and you're going to select one card from the deck. There is a 4 over 52 probability that the card would be an ace. Now, if I told you that it is raining outside, that really doesn't have any effect at all over the probability that was just computed there, right? It's still going to be 4 over 52, or 1 over 13 if you simplify. So that would be an example of a situation where you'd have independent events. Problems 30 and 31, we want to determine if the events are independent. On problem 30, event A is the event that you earn $50,000 in a year, and event B is the event that you were born in December. So this would be an example of independent events because the occurrence of one event does not affect the other. In other words, just because somebody earns $50,000 in a year, like that has nothing to do with the month that that person was born in. And vice versa, if somebody is born in December, that has nothing to do with the amount of money that they'll make in a given year. Now in problem 31, event A is the event that you earn an A on the next statistics test, and event B is the event that you study for the next statistics test. That would be an example of dependent events because the occurrence of one can have an effect over the other. In other words, if you get an A on the next test, maybe it's because you studied for that test. And vice versa. If you study for the next test, like it could have a direct effect over what letter grade you end up getting on the test. So we would have dependent events in that situation. There's a caution statement next, which is super important. It says, independent events are different from mutually exclusive events. Students sometimes want to think that these terms are the same, and they're not. Don't get confused with that. Mutually exclusive events, again, just means that the two events cannot occur at the same time. Independent events is different from that. Problem 32 is an example of the caution statement right above, and we're going to draw a Venn diagram for representing problem 30 here. So I've got that set up, and anybody who makes $50,000 in a year is going to be in this first circular region. Anybody who is born in December is going to be in this other circular region. Okay, now we've already said that these events are independent, but these events are not mutually exclusive, because it is possible for somebody to make $50,000 in a year and also be born in December. So there are people in the world that would be in the overlap of these two events. In fact, there's a note: if two events are mutually exclusive, then they're also dependent. That will always happen. Problem 33 is an example. It says to draw a Venn diagram showing the possibilities for the day of July 4th, 2030. Okay, and that's going to serve as an example of the note right above. So I've got my Venn diagram set up. What day of the week does July 4th, 2030 fall on? Well, there's going to be 7 options representing the 7 days of the week. Now, clearly in this problem we would have mutually exclusive events, right? Because it is not possible for July 4th, 2030 to fall on a Monday and also on a Thursday, for example. And so I've got these regions that don't overlap, like I had up here. Days cannot overlap. Okay, so that's why we would have mutually exclusive events in this case. We would also have dependent events, because dependent events means that the occurrence of one event does affect the probability of the other. And so in this problem, if we know that July 4th, 2030 falls on a Monday, that has a direct effect over what we know about the other 6 days, and that we know that that holiday does not fall on any of the other 6 days. Okay, so this problem here would be an example of dependent events, and mutually exclusive events will always mean that you have dependent events.